Okay, next section is 1.2. We're going to talk about functions and some properties of those functions, like domain and range, function notation, continuity, whether they're increasing or decreasing, whether they're bounded or unbounded, and things like that. Okay. Hopefully this will help you with your basis of understanding math applications that you can use elsewhere. We'll see. Okay, so function, domain, and range. Domain is all the values that you input into a function, and range are all the values that you get out of a function. So typically we'll use x for our input variable and y for our output variable, or in this case we'll use function notation. So we'll use f of x for y, that will be our range, and we'll use x for our domain. Okay. This is just simple mapping to show you like what is a function and what's not a function. So like for example, if you have something like this where every x value is matched with a y value, you can have an x value that's matched with the same y value. What that looks like on a graph is this. You have two different x values matched with the same y value. That's just 2 points that are, happen to be on the same horizontal line, which is fine. What you cannot have, though, by definition of function, this is really important, you cannot have one x value that has two different y values. So that's one x value that has two different y values like that. That violates the definition of a function. That's really important. Okay? It doesn't pass the vertical line test, which is what we'll use. And the reason we can't have it in math is because it's not helpful to have a function that when you plug in a value, you get different answers as the output. That's not helpful. That's not something that we could use in the real world, right? We want a function that when we plug something in, we get one unique thing out, right? Like, what is the predicted value in the year 1990 of something? Well, we get one thing out, not two different things. So that's really important that you don't have one x value paired with two different y values, like you see here in this mapping diagram. Okay, here's some examples from graphs. Like, if you look at these, it's really easy to use the vertical line test. That is a function because it passes the vertical line test. This is a function because it passes the vertical line test. And this is not a function because it does not pass the vertical line test, as you can see. A vertical line, if you plug in that x value, you get three different y values out. So that's the vertical line test, which we will be using. It's because it's probably the most reasonable. Okay, the next thing is the book mentions relevant domain. And we'll talk about that. It's not something you're going to be tested over, but sometimes specific problems have a relevant domain based on the context of the problem. So like for example, if we're doing a problem with temperatures, you might want to use like integers for your domain instead of real numbers because we don't typically give temperatures as like negative 0.7 degrees, right? We'll say negative 1 degree. Things like that. All right, so let's do a couple examples then. Let's find the domain of this function right here. So we can stick any value into a function. The only thing you have to look out for when you're looking at domains is two things. I'll write those two things down. First thing is you cannot have negatives under radicals. Okay, that's super important. These are important things that you have to look out for when you're talking about the domain of a function. Second thing is you cannot have zeros under a fraction or in the denominator of a fraction. Okay, so those are the only two things we have to worry about in this class for domain. We have to look out for negatives underneath square roots and zeros in the bottoms of fractions. That's it. Everything else we can do whatever we want. We can stick in whatever number we want and do a function. So here's an example then. If we look at this function, we know we don't have any fractions here, so we don't have to worry about number 2. We do have to worry about number 1 here, though. We have a radical. So we have to have what's underneath the radical be bigger than or equal to 0. Would you guys agree? Let's solve this then. We're going to subtract 2 from both sides, and we have x is greater than or equal to negative 2. So that's telling us that all the x values have to be bigger than or equal to negative 2. That's our domain. If we wanted to write that in interval notation, we would write negative 2 to infinity. We use a square bracket here and open bracket here. And this is the way I'd like you to write it because our book uses interval notation and so does WebWork. All right, let's try another example then. Let's find the range of the function now. So we want to look at all the y values that we can get out. So for domain, we know that we have issues with We know that x cannot be 0 here with the domain, because that gives us an undefined value. That's the only restriction on the domain. So if we did write the domain for this one, it would be all real numbers except 0. It doesn't ask for that. It asks for the range, though. Now, I typically graph these functions when I'm looking for the range. Now, this function happens to look like this. It's a hyperbola. You can graph it in Desmos if you want.
Yes.
So you can see that this is what 2 on Desmos, this is what 2 over x looks like. It's a hyperbola. And we're asked for the range. The range is all real numbers except there's one value that we cannot have, which is that value at 0. That value is a horizontal asymptote that the function approaches. So the function is not defined there. So we would have to throw that out. So our range is, we would say, we can say this different ways. We'd say all real numbers, but y cannot be equal to 0. Now, with interval notation, we'd say it like this: negative infinity all the way up to 0, not including 0, as well as, union, 0 to positive infinity, not including positive infinity. That's the better way to write it right there. You could use the word or in place of union as well, but it means both. What the word or means in math, it means both this branch and this branch. So if we look at a number line of what this range looks like, it's all real numbers except for 0. So there's 0 right there, and here's negative infinity this way, and there's positive infinity. So it's all real numbers, so we highlight all of this to the left and all of this to the right, except for the number 0. All right, so continuity then, there's different types of continuity. This function right here looks like a 4th degree polynomial. It's like f of x equals x to the 4th minus 3x plus 2 or something, I don't know. But it's a 4th degree polynomial where there's 4 real zeros, and it's continuous. There's no places that x is not in the domain. So the domain's all real numbers. This one right here has a hole in it, so it's got what's called removable discontinuity. I probably won't test you over that vocabulary, but if this vocabulary shows up on web work, I want you to know what it means. All right, so that's removable discontinuity. Jump discontinuity is where a function goes to a completely different spot. And then infinite discontinuity is like on a hyperbola where you go from like negative infinity down here all the way up to positive infinity as you move left to right in your domain.
Hey, Mr. Jones.
Okay, here's a quick example then. Which of the following figures shows functions that are discontinuous at x equals 2? Obviously, this one right here shows that point of discontinuity. So that's hopefully a pretty easy problem. Increasing and decreasing is also something I'm going to ask you guys. And this function right here is always increasing. This function right here is always decreasing. This function is always constant. And this one has 3 different. It's decreasing on this interval from negative infinity to negative 2 right here. But then it's constant from negative 2 to positive 2. And then it's increasing from 2 to infinity right here. All right, so I'm going to ask you guys to do problems like that in web work. I'm also going to ask you guys to look at piecewise functions. Okay, here's an example of a piecewise function right here. And we can identify on the intervals in which f is increasing, decreasing, or constant based on this. So let's graph this real quick. This function looks like this. It's negative 5 if our x values are less than or equal to negative 3. So negative 5 is 1, 2, 3, 4, 5, right down here. So here's 1, 2, 3. So it's negative 5 all the way up until this point, negative 3, where we have a closed dot because that's less than or equal to. Then it's a line 2x plus 1 in between negative 3 and positive 2. So 2x plus 1 has a y-intercept of 1, has a slope of 2. So it goes up 2 over 1. So in this case, it'd go down 2 over 1, down 2 over 1, down 2 over 1. So then it's this line right here, all the way up to 2, where we have an open circle at 2. And then it becomes this, it becomes 5. So 4, 5 right here. If x is greater or equal to 2. So you have a closed circle there, and it's the horizontal line. So that's what that looks like right there. A couple more things then. Bounded. We'll talk about bounded. Functions are bounded below or above. So like, for example, when we do an exponential equation like this, this is unbounded above, but it's bounded below. Okay, or if we study logistic, one of the 12 basic functions we'll have is a logistic function, which looks like this. And that is bounded above and below. Okay, so this would be the upper bound, this would be the lower bound, and so on. Hopefully that's pretty self-explanatory. Okay, local and absolute extrema, these are max and mins. Okay, so we have local maximum, which I think you guys called relative maximums and relative minimums in Algebra 2. So like for example, if you have this right here, this is a 4th degree polynomial that's been shifted up a little bit. This point right here would be an absolute minimum, and this point right here would be a relative minimum. It's the minimum point on a relative interval, but there's a point lower over here. So that's an absolute minimum, and that's a relative minimum. Okay. Let's do one example of finding these then. Here's the function we'll use right here, x to the 4th minus 7x squared plus 6x. Let's find any local max or min, and the values at which these occur. Okay, so let's graph this real quick. I'll just graph it on the calculator. Okay, so if you graph this 4th degree polynomial right here, here's what it'll look like. I had to adjust the window, so there's what the window will be to get a good graph. But here's what the graph looks like. And from this graph, we can get the absolute maximum or minimum and a relative minimum right there, which is what they want. To do that, we do second calculate. We're going to do minimum, which is 3. We have to scroll to the left of the absolute minimum and hit enter. And then scroll to the right of the absolute minimum and hit enter. Hit enter for the 3rd time, and that gives you negative 2.06, it looks like. So x equals negative 2.06 is the absolute max. And then the other one occurs over here, which is the relative one. Second calculate minimum again, 3. You have to scroll all the way over there. Hit enter. Enter, and then enter. And that gives you the relative one, which gets at 1.6. I can't tell if it's an 8 or a 0 on my calculator, but on your calculator you'd be able to read that. 1.68. Let's go with. So that'd be the relative minimum. All right. Next, symmetry is pretty simple. You guys know that symmetry is if this point xy is on the graph, and the point negative xy would also be on the graph if it's symmetric about the x-axis. So even functions have this property of symmetry about the x-axis. Okay, or y-axis. I'm sorry. Symmetry about the x-axis would be the point xy is on there, so is the point x negative y. So we can use this as an algebraic test, which we'll do later for symmetry. Okay. We'll also deal with horizontal and vertical asymptotes, which brings us to limit notation. And this might be the first time you guys have seen this. So what this means, as x goes to negative infinity, the function equals a value, and as x goes to positive infinity, the function equals a value. So let me give you an example. If you have a graph right here that goes like this, it's an exponential function, like y equals 2 to the x, for example. All right, then we could say that the limit of this function, I'll call this function f of x. The limit of this function f of x as x approaches negative infinity is 0. What that means is, as we go towards negative infinity with our x values, the function approaches 0. That's exactly what that means, and that's exactly what this function does. So let's try one example then of identifying horizontal and vertical asymptotes. On your formula sheet, if you pull that up, I have specific directions on how to find these. So on the formula sheet under chapter 2, horizontal asymptote, there's 3 steps if the exponent's the same. Basically, if it's higher the top, or the bottom of the top, or if it's higher the top. In the vertical asymptotes, these occur as zeros in the denominator. So let's find those first. For this one, vertical asymptotes occur at zeros of the bottom. So we're going to factor the bottom. We're going to make this x over and factor into 2 linear factors. X minus 2, x plus 1. So the vertical asymptotes are at x equals 2 and x equals negative 1. So we'll take a look at that graph real quick. 1, 2 is right here, and negative 1 is right here. All right, so if you graph this, this is what you got. 2 vertical asymptotes, 1 at negative 1, 1 at 2. And there, you can tell there's no horizontal asymptotes. But if you look at the formula, on the formula sheet, when you have an exponent that's higher in the bottom, then horizontal asymptote is like y equals 0. So I'm sorry, there is a horizontal asymptote. It's actually y equals 0. And you can see the function goes to that here, and it goes to the left as well. So horizontal asymptote would be y equals 0. All right, so I hope this helps.